Students, now let us see another experiment in physics. This is also from the section electricity. What we are going to do, we are going to use the potentiometer, right. I will introduce you potentiometer here. Using the potentiometer, we are going to compare the electromotive forces of two different batteries, right. Two different batteries, how to compare the electromotive forces is what we are going to do here. So, let me introduce potentiometer for you. Potentiometer will have a string like this, simple, and with this string, right, this string can be 1 meter, 2 meter, 3 meter, 4 meter. The one we are going to use has 4 meter length string, and this will be connected to a battery, a variable resistance and a switch. So, what will happen, let us say I am using a 4 volt resistance, and let us say I have adjusted the resistance variable 4 volt battery, and the variable resistance has been adjusted such that the resistance of this string is equal to this, then you will have 2 voltage here, 2 voltage here, correct. So, how many voltages we are going to have here can be decided by these two. One is you can increase this, then obviously the voltage that drops into this string will increase, or else you can change this resistance, because this resistance and the string are in series. So, according to the proportion of their resistances, the voltage will fall into each of them. So, suppose if 2 voltage falls here, and if it is a 4 meter length, now let me mark some voltage points, look at this. Let us take this point as 0 voltage, then here it is going to be 4 voltage, assuming no internal resistance. It is 4 here, right. If 2 voltage drops here, this point has to be 2 voltage, and another 2 drops here, it is 0. So, from 4 voltage to 2 voltage, the voltage drops across this 4 meter length string, and it will drop uniformly, because same way in the meter bridge here also this is having a uniform cross section. The string has uniform cross section. If uniform cross section, then the resistance of the string is going to be rho L over A. Rho is the resistivity, L is the length, A is the cross section. So, if A is constant, rho is anyway constant, R and L will be proportionate, right. So, with the length, resistance will increase proportionately. Therefore, the voltage also will drop proportionately with the length. That means, if you take the midpoint, right, midpoint, that will be 1 voltage. Midpoint of these two, it will be 0.5 voltage. Midpoint of these two, it will be 1.5 voltage. Understand? It will equally, uniformly fall across this string. This is what we call potentiometer, very simple, right. A simple name for that is potential divider. So, the potential is divided, it is distributed along a string. So, suppose you need only 0.5 voltage gap, you can connect these two, then you get 0.5 voltage. You need 1 voltage gap, then you can connect these 2 points, then you get 1 voltage gap, right. Okay. Having such a potentiometer, now what we are going to do on this potentiometer, look at this carefully. We take a wire, divide it into 2. These are the 2 batteries of which the electromotive force has to be compared, right. Right. I will explain what that is. That is a two-way switch. This is a very high resistance galvanometer, and you are going to bring it here. This setup is the usual setup to protect the galvanometer, you know that we have a high resistance. What we have here is a two-way switch. what we have here is a two-way switch. That means when I close it to this side, it connects to this battery. When I close it to the other side, it connects to this battery. Let's say this is E1, this is E2. Right? Now, let's say you have connected to E1, that side is connected, and you have found a point where galvanometer shows 0 reading. We are familiar with galvanometer, we know how to get 0 reading, equilibrium point, all that we know. So, you find a point where galvanometer shows 0 reading. So, let's say that length is L1, right. So, I can write a formula, see the voltage drop in L1 in this circuit, the voltage drop in L1 and E1 must be equal. That is why you do not have reading through the galvanometer. Why? These 2 points are at the same voltage. Then if you do not have a flow through this, these 2 points also must be at the same voltage. Let us say this is 4 voltage. Suppose you have 1.5 voltage drop here, then this is going to be 2.5. Then you have to keep this point at 2.5. This is 4, 2.5. It won't be 0.5, right? These values are wrong. This is 3.5, isn't it? Because 4, 2, in the middle is going to be 3, it's going to be 3.5, right? 3.5, 3, then it's going to be 2.5. Because 2, 4, it increases like this. So, if you have 1.5 voltage drop here, this is 4, this is 4, this is going to be 2.5. Then, if you keep this at 2.5 only, galvanometer will have 0 reading, 2.5, 2.5, there won't be any current. So, look at this 4 to 2.5, 4 to 2.5, the equilibrium will happen. So, when galvanometer shows you an equilibrium, I can say E1 and the voltage drop here, that is within L1, has to be equal. But that voltage drop, let us say V1, that is proportionate to L1. I explained that because you have a uniform length and all that. So, with the length uniformly, proportionately, voltage is going to drop. Therefore, E1 will be proportionate to L1. If you want to make it equal, I can say E1 equals K L1, where K potential gradient. Potential gradient means how much of potential drops per centimeter, right? Voltage per meter or centimeter. How much of voltage drops for every meter or every centimeter. Let us say you have 0.1 volt, okay, I will calculate here 2 voltage drops, 4 to 2 voltage in 400 centimeter. So, you get 1 over 200, that is 0.005 volt per centimeter. So, every centimeter the voltage drops by 0.005. Suppose you got the length to be 100 centimeter, then this into 100 you will have 0.5 voltage drop. Suppose you get the length to be 250 centimeters, this into 250 you will get 1.25 voltage drop. So, K is what we call as the gradient of potential drop, right? Potential gradient or the potential slope, you can say, how the potential falls. E1 equals KL, KL1. Similarly, later you can change this two-way switch to the other side, E2. Now, this battery is going to be connected. For that battery also you can find the length where the galvanometer shows you 0 reading, then it will become KL2. KL2. E1 over E2 will be equal to, when you divide K and K cancel, L1 over L2. The voltage drop, potential gradient or voltage gradient, right? Voltage slope doesn't change because you didn't do any change in the setup there. In the potentiometer setup, you didn't do any change, right? Same battery, same resistance. So, the voltage drop, voltage slope doesn't change. So, K is constant, then L1 over L2. You know L1, you know L2. So, you know the ratio between E1 and E2. If you know E1, you can find E2. If you know E2, you can find E1. right. So, that is what the practical is about. What is it? Comparing the electromotive forces of two batteries. I am comparing E1 and E2, E1 and E2, right. Materials and apparatus, a potentiometer, 2 voltage lead acid accumulator or two 1.2 volt nickel cadmium cells connected in series. A Leclanche cell, a Daniell cell, these are the two cells, two batteries that we are going to compare. A Leclanche cell, right, which has an acid in it, high concentrated sulfuric acid we usually have, and a Daniell cell, that is a tricell. Center 0 galvanometer, two-way switch, two plug switches, 5 kilo ohm safety resistor, a sliding contact, connecting wires. So, since you are familiar with these electricity experiments now, you know each of these parts, I do not have to explain them. Remember, always I say, when you are referring to these experiments, within a section, let us say now you are watching this experiment, make sure you have watched all the previous experiments within electricity. I have already done, I think, 3 experiments before this, right. This is the 4th experiment I am doing in electricity. So, when you are coming to this experiment, you must have watched and understood previous 3 experiments, because I make references to previous experiments. Certain things I explained there, I will not explain again here. For example, when we use the galvanometer, we use a safety resistor. So, what is that safety resistor, why we use that and all that? First time when we use galvanometer, I would have explained it. Second time, third time when we use galvanometer and the safety resistor, I wouldn't spend time explaining that. So, if somebody does not watch the first video, if you come directly to the third experiment, you wouldn't understand that. So, make sure when you are studying, when you are going through all these experiments, when you are in a section, within the section you study in the right order. Do not jump the order, you will not understand sometimes. Right, this is how the circuit is going to look like. I already have explained it. E1 over E2 becomes L1 over L2. Method. Set up the circuit as shown in the figure. The key K1 is closed while K2 is kept open. K1 is the switch to provide the supply to the potentiometer. K2 is the switch. K2 is the switch for the short circuit the safety resistor with the galvanometer. Initially we keep it open, we find the approximate equilibrium point, then only we close it. Connect the two-way switch to cell E1. Check the circuit by first touching the end A by the sliding key and observing the direction of the deflection of the galvanometer G. Then touching the end B of the wire by the sliding key and observing the direction of the deflection of the G again. Now that we have done in the previous experiments also, look at this. When you touch it here, if you bring it here, if galvanometer shows reading on this side, when you touch it on the other side, it should show reading on the other side. Then only the galvanometer is or the circuit is properly connected. Suppose in both cases, if you are getting the reading on the same side, possible reason sometimes this switch is not connected properly, then the current flows through this one only. So, always you will have same side, right, or else imagine if we have used only 1 voltage here and this is 2 voltages. So, if I take this point as 0, 0, 0, 0, it is going to be 1, but here you have 2 voltage drop, isn't it? Here you have 2 voltage drop. Then you won't find the equilibrium anywhere, because you need 2 voltage drop in the middle to get equilibrium, but here it does not have, the entire voltage drop is only 1 voltage. If that case is there, then in that case also both times you will have same side reading, both sides you will have same side readings. Why? Do you know why? Okay, if it is 1, this is 1, 2 voltage drop, this is going to be minus 1. So, if you touch it here, 1 minus 1, current flows downwards. If you touch it here, 0 minus 1, from there also current flows downwards. So, that case also the current might flow in the same direction. That means galvanometer will not show you deflection on both sides. So, before you start finding the equilibrium point, check that. Connect the galvanometer, like touch the ends of that string and see whether galvanometer shows you 2 sides readings. If it does not show, what could be the reasons? One, this voltage supply is not properly connected. The potentiometer does not get the voltage supply, or else potentiometer's battery E0 is smaller than E1 and E2, then you won't get it. Smaller than E1 and E2, you won't get it, right? So that's what they are talking about here, double checking whether the circuit is working properly. If the two deflections are in opposite directions, confirm the accuracy of the circuit. Now find the balance point for cell E1 in the usual way by first finding the rough balance point with the key K2, open, and then finding the accurate balance point after closing the key K2. We know that. Measure the balance length L1 and record the value. Repeat the procedure of the cell E2 by connecting the two-way switch to it and obtain the relevant balance length L2 accurately. Record the values. Very simple, that's all. E1, E2, connect them, find the equilibrium lengths. So you are going to get E1 over E2 equals L1 over L2. I am going to do like only one reading I am going to get, and I am going to find E1 over E2 ratio. But see, even this is possible. Now we can do like this. L1 equals E1 over E2 L2, right? We can go for a y equals mx graph. How do we get L1, L2 values? Change the gradient. What gradient? Voltage gradient, voltage slope. Across the string of the potentiometer, first you give 2 voltage drop, find L1, L2. Then change that. How do you change that? If you use a rheostat or variable resistance in the potentiometer circuit, when you adjust that resistance, the potential drop in the voltage in the string of the potentiometer is going to be different. So the potential slope, voltage slope will differ, K will change. When K changes, you will get L1, L2 values changed, right? So by changing the slope of voltage, you can get different sets of L1 and L2 values. You can draw the graph as well and get the ratio between E1 and E2. But in this experiment, since the procedure is same, we are going to repeat. I am just going with one value, comparing them, right? Shall we see how we are going to get these values? So the apparatus for this experiment, mainly the potentiometer. I'll explain you how to use this potentiometer. Have a look at it. There are two endings here. Can you see? Two knobs. Across these two knobs only we are going to give the voltage. We can give any voltage. It can be 2 voltage, 5 voltage, 10 voltage. Whatever the voltage we provide has to be provided in between these two knobs. And in between these two knobs, what is connected? Can you see here? There is a string. See, starting from here, a string. It goes all the way. Same string goes all the way up to here. Repeat, from here all the way up to here you have same string. And this full length of a string is 1 meter. 1 meter. We have a scale also. This is a scale we can measure. Like the meter bridge, on the potentiometer also you have a scale. This is 1 meter. And then it is connected to another string. Can you see? By a plate it is connected to another string. The second string also goes all the way up to the next side. So now it is 2 meter. There is a third string. That is another meter, altogether 3 meters. And starting from here, fourth string, 4 meter, altogether 4 meters. And that is what is connected to the other end here. So imagine if you give 4 voltage in between these two. If you give 4 voltage in between these two, that 4 voltage will be uniformly distributed across this string. 4 voltage in 4 meter. That means every meter 1 voltage will drop. Right, every meter there will be one voltage drop. That's what we call the voltage gradient. Voltage gradient. Per meter, how much voltage drops. Since this is a string with uniform cross section and the same string is being used, right, then the gradient will be same wherever you measure. That means every centimeter you take here will drop equal amount of voltage. Equal amount of voltage will drop at each centimeter here. Understand? So uniformly uniformly, evenly the voltage drops across the string. That's why another name for this is voltage divider. Because if you give 4 meter and if you go to the right middle of this string, altogether 4 meter is there. If you go to the 2 meter point, that will show you right middle of the voltage you have given. If you have given 0 and 4 voltage in between these two, the midpoint will show 2 voltage for you. Understand? So, another name for this is voltage divider. Our traditional name is potentiometer, right? So, that is what we are going to use in this experiment. And then we have the connecting wires. These are the wires that we will be using to connect all the equipments, connecting wires. This is a high resistance. What's the use of high resistance? I think I have mentioned in the previous experiments also. When we use high sensitive galvanometer, that means it can measure even small currents. It's very sensitive. Then you should not let high current flow through the voltmeter, flow through the galvanometer. Because high sensitive galvanometer, if high current flows through that, it might damage the galvanometer. So, to ensure that high current doesn't flow through the galvanometer, we connect a high resistance also in series with the galvanometer, so that very high current doesn't flow through the galvanometer. So, it's just to protect the galvanometer we do this. And this is a two-way switch. I'll show you how a two-way switch works. There are 3 portals here, 1, 2 and 3. So, 3 wires will be connected. One will be connected here, one will be connected here and another one will be connected here. When you close it to this side, this is how you close the switch. When you close it to this side, these 2 wires will be connected, these 2 will be connected. So, that will become a closed circuit and the other 2 will remain open. If you turn it to the other side, now the other 2 will get connected, these 2 will get connected, that will form a closed circuit and the other 2 will remain open, right. This is what we call two-way switch. We can switch it on either side of it. Again, when I connect it in the circuit, I will show you where we are going to use this. This is the plug key or insert key that we use. You know that how it works. If you remove this key, the circuit will be open. If you plug this in, circuit will be closed. We call it plug key or insert key. And this is the sender zero galvanometer. Sender zero galvanometer. It has measures both sides. It can measure electricity in both directions. The flow of electricity can be measured in both directions. Also, it's very high sensitive. That means even a small flow of current, say in microamperes, still it can measure it. Still it can measure it. So, compared to a usual ammeter, there are 2 differences on this. One is it's high sensitive. 2, it measures both directions. Ammeter, there is a plus and there is a minus. From plus to minus only the current will be measured, right. Suppose you have changed it. On the plus side, if you have given lower voltage, on the minus side of the ammeter, if you have given higher voltage, then the current flow is in the other direction, ammeter will not show it, right. Whereas this one, however, whichever the direction you connect it, it will show plus current and minus current, it will show. And this is the sliding contact. This is the sliding contact. How we use this sliding contact is, we will connect one end of it to the galvanometer and the other end I can touch wherever I want. Wherever I want on this potentiometer, I can touch it to measure the potential difference, right. Sliding contact. Careful, even though we call it sliding contact, you are not supposed to slide it on the string, because when you slide it on the string, it can damage the string. Sometimes the cross section might vary. It might damage the string and the cross section might reduce. If the cross section reduces, then you will not have uniform drop of voltage. So, ideal way to use this, even though we call it sliding contact, don't slide it, just touch it at a point If you want to move it, take it and touch it at another point. Touch it at another point. That's how we will be using it, the sliding contact. And then you can see these are the two cells that we are going to use. I said we are going to compare the electromotive forces of two cells. These are the two cells. This is the dry cell, the usual dry cell, usual battery. This is what we call Lagrange's cell, right? This is an acid battery basically. So we will be using these two and compare their electromotive forces. And this is our power supply. Using this only we will be supplying direct current to the potentiometer. I told you we will be giving a voltage here. That voltage is going to be given by the power supply, right? It has a switch, you can see it has a switch. So after connecting it, when I switch it on, the power will come into the potentiometer. This is all the apparatus we are going to use in this experiment. It's a very simple experiment. Now let me show you how to make the circuit for this experiment. First, let's connect the power supply to the potentiometer. Very simple. Look at this. Let's connect this to this point, which means you can see this is the plus. This is the plus, right? So plus I am connecting it to this point, right? So let's see how we can connect it. Let's connect it here. Similarly, the minus side of the power supply, minus side, let me connect it to the other end of the potentiometer. So here what happens, I have directly connected the power supply to the potentiometer. I did not connect a switch here because power supply has a switch. I can use the switch on the power supply. Suppose if you are using a battery instead of this, then you need to have a separate switch. It can be an insert key or it can be a tap switch. Some sort of switch has to be there because you should not let the current continuously flow through this string, the potentiometer string, because then there might be heating of the string happening. When the string gets heated, you know, with temperature, resistivity might change. Also, sometimes the string might get elongated, so the length and all will differ. Because of that, you should not let the current continuously flow through the potentiometer. Only when you want to take the measurement, switch it on, let the current flow, take the measurement. Right after that, switch it off. Right? That is one thing. Second thing, if you want to change the potential that drops into this voltmeter, either you can change it on this, you know, here there is a knob, you can change it 2 voltage, 4 voltage, 6 voltage, likewise you can change it. If not, you can have a separate rheostat in series with this. So if you have a rheostat, what will happen? Let's say you have set it at 10 voltage and then this potentiometer and a rheostat, you connect it in series. Then what will happen? That 10 voltage, part of that will fall into the rheostat, the rest of it will fall into the potentiometer. By changing the rheostat's resistance, you can decide, you can change how much voltage falls into the potentiometer. So if you want to take different cases, if you want to take multiple readings and if you are going for a graphical method, you can do that. You can have a potentiometer you can have a rheostat connected here. By changing the resistance of the rheostat, you can decide or you can change how much of voltage falls into the potentiometer. Here I am going to take only one reading, so straight away I have connected this to the potentiometer. Right. Then what do we do? You can see, let me take this battery. On this battery, the black color knob, that is the minus point of it, minus point. The other color, the brown color, or sometimes it can be red color, right? Brown or red color end will be the positive side of it, plus. In the potentiometer, this is where positive is. See, I connected positive to here. This is the positive. Let's connect both positives, right? Let's connect both positives. Right. I have connected the positive side of this battery to the positive side of the potentiometer. Let's connect the other battery's positive side also here, which means I can connect it here or anywhere in this wire I can connect it. So, let's connect that as well. Take the other battery. Take the other battery. This is where the positive side is. So, let me connect the positive side. Positive side. I have to connect it here or anywhere on this wire. Anywhere on this wire. So, I will connect it here. So, now what you can see here, both batteries positive side are connected here. Let me explain you how it works now, right? Before I complete the rest of the circuit, let me explain to you how it works. What I will do, I will take the galvanometer, connect one side of this galvanometer, let it be this black side, okay, does not matter which side, whichever the side. If I connect it with this plus side of this, minus side of this battery, look at this carefully, right. Right. What I have done now, I have connected the minus side of the battery to the galvanometer. Plus side of the battery is already connected to the plus side of the potentiometer. Then what I will do, I will take this sliding contact, right. Let me connect it to the other side of the galvanometer. Right. See, I will explain you the concept now, right. So, let us say 4 voltage has been given across the potentiometer. Then let me assume this point to be 0, then this will be plus 4, 0, plus 4, 0, plus 4. Along the wire, this plus 4 reduces uniformly, little by little it reduces. At some point it will be 3, at some point it will be 2, it will be 1, and again at this point it is 0. 4, 0. Right, let it be like that. Now, I have connected the positive side of the battery also to the same point where the positive side of the potentiometer is there, which means this is also plus 4 voltage, plus 4 voltage. If I assume this battery to be 1.5 voltage, I do not know, if I assume it to be 1.5, on the plus side if it is 4, on the minus side it has to be 2.5, correct, because 1.5 drop has to be there. E, the electromotive force, 4, 1.5 less, it will be 2.5, right, on this side 2.5. That is what I have connected to the galvanometer and I have taken from the galvanometer. Now, what I am going to do, I am going to touch this at different points on this potentiometer. I am going to touch it at different points and find out at which point galvanometer shows 0 current. At which point galvanometer shows 0 current is what I am going to check now. So, just assume at this point if I get 0 reading. Students, now you can see now it is showing a reading, that is because of this battery, because this battery is in the circuit. I have not given the power to the potentiometer. So, now it is not working as per what we want because I have not given the power to the potentiometer. So, just assume at this point if I get 0 reading, that means this point and the other side of the galvanometer are at the same potential, because if 2 points are there at same potential, there won't be current flow across them, right. So, I need to find out which point, at which point the 0 current is shown in the galvanometer. If I can find that point, let us say this point I get it, at this point, okay, then what it means is at this point same voltage as of the battery's minus point, because in between I have the galvanometer. Galvanometer shows 0 reading, no current. No current means this point, the minus point of the battery, and where I have it on the potentiometer are equipotential. I can find the potential of this point in the potentiometer, voltage of this point in the potentiometer, because I know 4 meters, 4 voltage, I can measure the distance and I can find out what would be the voltage here. I know the voltage gradient, right? At what rate it reduces, how much distance it is, I can find it. By finding that distance, then I can find what is the potential here. If I find the potential here, I can find the potential difference across this battery. If it is E, I can say KL would be equal to E. What is K? K is the voltage gradient. Per meter, how much of voltage drops. L is the distance from this plus side. What is the distance up to this? From this plus side, suppose if this is a point, you can say up to here it is 100. Look at this from here. In the first wire, it's 100. And in the second wire, let's say it is 60. Then 160 centimeters would be the length. K into 160 E. Then what I will do, I have done this for this battery. I will repeat that for the other battery. I will remove this, connect it here and repeat the process so that I can find the E of this one for what length of potentiometer it balances. So let's say this is E1 and the length is L1. E1 equals K into L1. And let's say this is E2. Then E2 equals K into the length for that, let's say L2. E2 equals KL2. E1 KL1, E2 KL2. Divide the equations. E1 over E2 equals K and K will be nullified on the right hand side. You will have L1 over L2. So the electromotive forces ratio will be equal to the ratio of the lengths that I have got on the potentiometer. Is it understandable? This is what the concept. This is precise. This is better than using a voltmeter to find the voltage across this. Better than that, because here we ensure there is zero current. Zero current. Voltmeter doesn't ensure zero current. There might be a small microampere even. Right. So here it's absolutely zero current. Therefore, E perfectly you are measuring it here. Only thing is, when you are measuring it, sometimes there might be measurement error, reading errors. To avoid that, what you can do, you can change the voltage across this voltmeter so that the K changes. Then after changing K, you can take multiple readings. By changing the voltage across potentiometer, you can take multiple readings and you can go for a graph. You can go for a graph. So graph, and from the gradient of the graph, you can find E1 over E2. Here I am not going for a graphical method. I will just get one reading. If you want a graph, matter of repeating it multiple times, getting multiple points and going for a graph. Understood? Right. Other thing, since I have to remove this wire and connect it here every time, it might be hassle for us. That is why I am going to use the two-way switch. See how we use the two-way switch here. This is the two-way switch. Right, that's a two-way switch. On the two-way switch, the wire from galvanometer, let me connect it in the middle. Look at this, the wire from galvanometer is connected in the middle. Then I'll take one wire from this battery, connect it to one side, another wire from the other battery, connect it to the other side. See how it works? Let me take one connection from the minus side of this battery and let me connect it to this side. So you must understand, if I close it here, this dry cell is going to be connected to the galvanometer. Can you see? Dry cell. Can you see that? These two are connected. What is this? This goes to the dry cell. What is this? This goes to the galvanometer. This goes to the galvanometer. Right. Now let me take another one from the minus side of the Lagrange cell. I'll connect it to the other side of the two-way switch. Other side of the two-way switch. So now you can see clearly. I can fold it to either side of it. If I fold it on this side, it connects to the Lagrange's cell. If I connect it to the other side, it connects to the dry cell. So galvanometer can be connected to dry cell and Lagrange's cell without changing the circuit. Just by switching this particular two-way switch both sides, you can connect it to the batteries. And the other thing which I already mentioned, now we need another resistance in series with this galvanometer to protect this galvanometer from high current. Let's connect that. Rather than giving it directly, let me connect it to the switch, or let me connect it to the resistance. From the resistance, let me take it to the galvanometer, so that galvanometer will not get high current. Right. Another thing you know, after we found the approximate point where zero current flows, then better if we short circuit this resistance so that the value of current increases. Right? So that the value of current increases and we can accurately find the point where the current is zero. So you need to have another mechanism to shortcut this or short circuit this when you want. That is where we are going to use this switch. So let me keep that switch as well. Let's connect it in between these 2 points parallelly. Right? Let me keep it open now. After finding the approximate point, I'll close it. Right. Now, the switch is parallel to this resistance. Whenever I don't want the resistance to function, I can close the switch so that the current will comfortably flow, because when I close the switch, it has almost zero resistance. Compared to 500 ohms, zero resistance, all the current would go through zero resistance because they are in parallel. When I keep it open, that's infinity resistance. Compared to infinity resistance, 500 ohm is better, current would flow through 500 ohms. This is all the setup is. Now let me set it at 4 voltage. Can you see this is already at 4 voltage? Fine. Let me switch on. Let me switch it on. So let me first close it to one side. Right. When I close it to this side, you can see which cell is connected. See? The dry cell is connected. See, the dry cell is connected. So when the dry cell is connected, let's see at which point we get the equilibrium or equipotential points. See, when I keep it here, positive current. Can you see? Positive current. At this point, it's negative current. Negative, negative, negative. So in between this point and this point, there is going to be a 0 point. Still positive. Here it's negative. Can you see? Negative. Positive. Positive. Negative. Positive. Negative but close to 0. So approximately at this point we are having 0. Approximately at this point we are having 0. Right? Now what I do, let me close this switch so that the resistance is short circuited. Now let's find it. There is still a small difference. Look at this, guys. Look at this, students. Here, plus, minus, minus. That's the point where we get 0. Yes, that is where it's 0. This is for the dry cell. And after finding the point, we will switch off the power and find out it is at 76. From this side, it's 76. From this side it's 76. That means starting from the positive side, 100 and a 76. So altogether 176 centimeter is the length L1, that is for this battery E1. What is the next step? We can write this as E1 equals K into 175. Next we are going to do, change this to the other side, but make sure you remove this switch, you open this switch so that the galvanometer is protected. Change the two-way switch now. Change the two-way switch to the other side. Now the Lagrange cell is connected. Switch on the power supply. Right. Let's check at which point we get equilibrium. Positive, positive, negative. Yeah. Still negative. Positive. Somewhere around this point we get it 0. Approximately that is where it is 0. What do we do now? Short circuit the resistance. Now check that. Minus, plus, plus, minus, close to 0, not yet exactly 0. Right, that is the point where we get 0, 0, that is at 1, from this side it's 92.5, that means from here it is 7.5. This point, you need to check from which side you have to measure. It is from this side, it's 7.5. How? Look at this. First line goes all the way starting from here to here. Look at this, from here to here, 100. And then another 100. Now from here I have to measure it. From here it was 7.5. So 207.5 centimeter is what we are getting as the L2. L2 is for which one? For this cell. Right? 207.5 centimeter. Now we can write E2 equals same voltage gradient K into 207.5. So E2 equals K into 207.5 centimeter. You are using same K for the first case and second case because the gradient, the voltage we supply to the potentiometer is same, the length is same. So V over L is what we call K, that is same. So E1 over E2, when you divide it, K and K will get cancelled. You will have L1 and L2 only. Using that, you can get the ratio E1 to E2, L1 to L2 ratio, you can get it. Suppose out of E1 and E2, if you know one of those values, if let's say if one of these values is known, the other E can be calculated from this. Right. So this is all on this experiment. Now let's write down these values and calculate E1 over E2 and see what ratio we are getting in between the electromotive forces of these two batteries. You can see the readings that we have got. I have written here L1 is 176 and L2 is 207.5. So E1 over E2 has to be L1 over L2 as we discussed earlier. Get the ratio. That's, let's say, 1760, 2075, 0.8, 8540, 56, 60, 16. 10,000 approximately you get 5, right? 0.85 is the ratio. 0.85 is the ratio. So if E2 is 1.5 voltage, you can multiply and get E1. Or if E2 is 2 voltage, you can multiply and get E1. Right? So that's what the calculation here. Nothing much here. We didn't go for a graphical method. It was just the ratio calculation. We got L1, L2. That's what the ratio is. Usually in the exam questions, they will give one of these E and they will ask you to find the other E. So you can cross multiply and get the other E. Clear? So that's all in this experiment. Now let's see how this has been tested in the previous exam papers. Alright, now let's see some past paper questions from this. I have taken a very old one, 1980 paper. The circuit diagram shows the potentiometer arranged to compare the electromotive forces of two cells X and Y. What is the main advantage of using potentiometer for this purpose? Right. So, what is the main advantage? Why can't we take the voltmeter, take why can't we do like this? You take a voltmeter or multimeter, take the battery, connect it and find the EMF, and the other one also find the EMF. Why can't we do like that? Here you assume, when you calculate or when you get the readings, you assume voltmeter doesn't take any current. You assume there is no current that goes through voltmeter. But actually there will be a current in this circuit. So when there is a current in the circuit, what you are going to measure is E minus IR, not E. Since there is a small current, because voltmeter wouldn't have infinity resistance, it will have a small resistance, it will have a high resistance but not infinity. So high resistance means at least in nanoamperes there will be some current in this circuit. Whereas when you complete the circuit here, when you get the reading after the balancing point is found, through the battery no current flows. There won't be any current flow through the battery. So the IR part will not be there. Only E will be there, since there is no current, because I is going to be 0. Understand? So let's write, when it is balanced, or when the galvanometer shows 0, there is no current through the batteries or through the cells. Therefore, internal resistance doesn't affect the value. Clear? Next, what should be the main characteristic of cell A? Cell A, which is cell A, this one. What should be the main characteristic of that? The cell that is used to supply the voltage to the potentiometer should be able to remain without running down for a long time. Until we finish the experiment, it should be able to provide the same voltage supply. Right. So let's say it should remain without running down. Without running down means staying in the same voltage, remain without running down for a longer period. Next, state a reason for not being able to find equilibrium point for cell X in the experiment. If you are not able to find an equilibrium point, what could be the reason? What could be the reason? Right? Possibly the voltage drop across PQ can be less than that of X. For example, see, if this is, let's say this is 2 voltage. So let me assume this point as 0, this point 2. So 2 here. Suppose if the total voltage drop across PQ is only 1.5, then here it is going to be 0.5. So you keep this slide at this point, 0.50, current will flow this way. You keep it here 2 and 0, again the current flows in the same direction. So you won't ever come to 0 point, because there is no 0 voltage point here. Right. So one possible reason could be either you can say voltage drop across PQ is less than the EMF of battery, or else battery A's EMF is less than battery X's EMF. Even that is a possibility. So let's say voltage drop across AB is less than the EMF of cell X. Next, high resistance R is a safety object for the galvanometer. Explain how this object should be used. So, what do? We have a switch for that. Yes. So, keep the switch S open and let the current flow through the resistance until you find an approximate or rough balancing point. After you have found the rough balancing point, then you can short circuit this resistance with switch S, close the switch and then find the accurate point. Let's write it. Keep switch S open and let the current flow through R until approximate balancing point is found. Until approximate balancing point is found. Then short circuit R by closing S and find accurate balancing point. Accurate balancing point. Next, why isn't the resistance of galvanometer considered in the calculations? Through the galvanometer, there is no current. When you are taking the readings at equilibrium or at balancing position, through galvanometer, there is no current. Then whether galvanometer had a resistance or not doesn't matter, right? So, let's say at equilibrium, there is no current flow through, there is no current flow through the galvanometer. Therefore, whether it has resistance or not, or the value of resistance doesn't matter to us. What is the purpose of rheostat R in this experiment? Where is rheostat R? It's there. So, by changing this, you can change the voltage gradient across PQ. I wrote that as AB somewhere, we have to change it as PQ, PQ. So, you can change the amount of voltage that drops here, right? Voltage gradient can be adjusted. Why do we have to adjust it? If we are going for a graphical method, we need different pairs of values, X and Y, the balancing length, let's say L1, L2. You need multiple pairs of values for L1 and L2. How do we get that? By changing R and then thereby changing the gradient, voltage gradient. That means how much of voltage drops here. That can be adjusted. Why is that? Because this resistance and this string are in series. So, keeping the battery unchanged, if you change this value, the proportion will change, right? The resistance of PQ and R, when the proportion changes, the voltage that falls across those resistances also will change according to the proportion. So, let's write it. What's the purpose of rheostat R in this experiment? By changing R, the voltage gradient across PQ can be changed. This will help to get or to obtain multiple readings and drawing a graph. Next, the electromotive force of cell X is 1.5 volt. The equilibrium point for X is in 30 centimeter. If the EMF of cell Y is 1.8 volt, where would be the equilibrium point for Y? See, X is 1.5 volt. So, we'll write like this. Electromotive force of the battery is going to be equal to K into L. K is the voltage gradient, L is the length. 1.5 volt, K into 30. Second one, 1.8 volt, K into L. I don't know. They are asking the L only. 2 divided by 1. 1.8 over 1.8 over 1.5. 1.8 over 1.5. K cancelled, 30 by L. L will be equal to, look at this. This is going to be 1.2. Isn't it? Other way around. L by 30 here. I am dividing the second one by first one. Careful. L goes up, 30 comes down. Correct? So, it's 20. 20 into this, 36. 36 centimeter. Obviously, since Y has a bigger electromotive force, the balancing length also has to be longer than the previous one. So, previous one had 1.5 volt, 30 centimeter. 1.8 volt has to have something longer. So, 36 centimeter is a possible answer for that. Either you can write E equals KL and do it, or else you can write like this. E is proportionate to L without K. Then you can say 1.5 is proportionate to 30 centimeter. 1.8 is proportionate to L. Divide it. When you divide, the proportionate cancels and becomes equal. And then from this you can get L is 36. Understand? Right? So, that's a very simple straightforward question on using the potentiometer to compare two batteries or two cells electromotive forces tested in 1980, so many years back. Let's see another past paper which has come after this 1980. The next one is on 1987 paper. Yeah, 1987. There is another question. Let's check that. Right, 1987. The figure shows the arrangement of a potentiometer with sliding contact. What should be the important characteristics of the following components for the potentiometer to give accurate readings? Look at this. Where is the figure? Right. So, this is the potentiometer string. This is the battery. They are asking about these two only, right? They are asking what should be about cell P and string AB. In the last question also they asked what should be the primary characteristic of that cell that supplies voltage to the potentiometer. It should be able to last longer with the same EMF. That means it should not run down faster, right? So, should be able to remain with the same EMF for longer time. String AB. What do you know about string AB? It has to have uniform cross section because R equals rho L over A. If the cross section is uniform only, then you can say R is proportionate to L. If R is proportionate to L only, then you can say voltage drop is proportionate to length. You measure the length and say, okay, length is this much, therefore this much voltage must be inside. To say that, to have uniform voltage gradient, the cross section has to be constant throughout. If it changes, everything will change. So, string B, uniform cross section, right? You are given a standard cell X with EMF of E, a box with high resistance R, a cell with unknown EMF Y, a high sensitive galvanometer, a sliding contact and connecting wires. In the given diagram, draw the circuit that you can use to scale this potentiometer. Okay. So, what we will do, they say a standard cell X with EMF of ES, a box with high resistance R, a cell with unknown EMF Y, high sensitive galvanometer, a sliding contact. So, standard cell with EMF ES, so that is known, we will use that, right. Then galvanometer and the sliding contact. That's a switch. Am I right? You are given the standard cell X, let's name it, this is X, with the EMF of ES, a box of high resistance R, this is the high resistance R, a cell with unknown EMF. To scale the potentiometer, you don't need unknown battery. To scale it, that means to find out the K of it, you need the known battery. So, here they asked, in the given diagram, draw the circuit that you can use to scale the potentiometer. To scale, like to find out the scaling of this, you don't need the other battery. You don't need battery Y. You need only X, which has the known electromotive force. Unknown galvanometer G, sliding contact D. Galvanometer G, sliding contact D. Right. In the given diagram, draw the circuit that you can use to find the EMF of cell Y. Right. To find the EMF cell Y, now you will put Y here and the resistance R, galvanometer and D. Understand? But what we usually do is we will have both together X and Y, and we will have a two-way switch. When we want, we can connect it to X. When we want, we can connect it to Y. But actually, that's two different circuits. So, that's why they are asking you whether you understand it's two different circuits. One is for scaling, one is for finding the unknown resistance. Right. So, they test. If we have shown here with X and Y and two-way switch, you might not get the marks, because they clearly asked in the previous question for scaling X, for scaling the potentiometer. So, clearly, like the important part here, you don't need both batteries here, you need only one battery, that is also with known electromotive force, known EMF, that comes here. Then the unknown one comes later. What is the purpose of the box with high resistance? To protect galvanometer from high current, or to prevent high current flowing through the galvanometer. Next, write down a formula for E in terms of ES and the two readings you need. Show those two readings in the circuits B1 and B2. Okay. So, equilibrium point, let's mark these distances. Let's mark this as L1, right? When you are drawing careful, but this plus and this plus must be in the same side. Look, plus, plus. Suppose if the plus was on the other side, then here also you have to change it other way around, right? So, from the plus side to the touching point, L1 is the distance. That means like across the battery. See, battery has been connected in between these 2 points. Don't go and measure the other side. Across the battery, L1. Here also across the battery, L2. Then we can say, they say write down a formula. So, you know, E over ES, L2 over L1. Why? Y has E. So, E is proportionate to L2. Similarly, this has ES. ES is proportionate to L1. ES proportionate to L1. That's why I have written here, look, ES L1, E L2. Once the potentiometer is connected, when the sliding contact is kept on both ends of string AB, sometimes the galvanometer will show deflection on the same side deflection. Give two reasons for this observation. Let's go back and see, right? What could be the reasons? You touch here, both cases you get the reading on the same side. What could be the reason? Possibly, one could be you have not plugged in this switch. So, if this plug is not switched, always the current is going to flow in the same direction. The plug key, right, if you forgot to plug that in, then this battery is useless, right? This part of the circuit will be useless. Only through this part you will have the current. Or else, second possibility, the voltage given by this battery P is smaller than this voltage. Say this has 3 voltage, this has 2 voltage. Imagine if this is 3, this point is 0, 3, 3. And this is 3, 3, 3, 3, 3. But this has 2 voltage, then you will have 3 minus 2, 1. This is going to be 1. So now look at this, this point is 0. If you keep it here, it's going to be 1. This is 1. So 1 to 0, current will flow. At this point it is 3, 3 to 0, current will flow. So always the current will flow towards the battery only. Understand? So one possibility, that's what we wrote in the previous year's paper. So they asked this, one possibility, P doesn't have sufficient battery, sufficient EMF. That means P's EMF is smaller than the X or Y's EMF. If not, switch is not plugged. Right, let's write it. First one, they asked 2 reasons. EMF of P is smaller than E or ES. 2, switch. Do we have a name for the switch? S. Switch S is not plugged in. Right, if it is not plugged in, or you can say switch S is not closed. Next, it is not advisable to hold the sliding contact on the potentiometer string for a longer time. See, we just touch it and take it, touch it and take it, touch it and take it. Why don't we keep it for a longer time and observe? Look, when you keep it for a longer time, if you keep it for a longer time, through this the current will flow for a longer time. If the current flows for a longer time, the electromotive force of the battery will change. To ensure you don't let the current flow for a longer time, we avoid it. Okay. Explain why. If the current flows through the galvanometer, or through, let's say this way, if the current flows for a longer time, batteries X or Y can run down. To avoid this, the sliding contact or the slide should not be in touch for a longer time, in touch with the string for a longer time. Clear? So understand, we are trying to protect X and Y, not the battery P, because battery P, the moment you have plugged in the switch, it anyway the current is going to go on. Whether you touch the slide or not doesn't matter. Whether slide touches the string or not doesn't matter. Battery P is going to give the current continuously. The slide touching the string or not will decide whether current flows through X or Y. Look here, X or Y. Through this, whether the current is going to flow or not is going to be decided by the contact here. For that only we are saying, make sure you don't hold it for a longer time. Next, if you are given an additional resistor box with suitable resistances, show in a diagram how it could be used to improve the accuracy of the potentiometer. Look, we already had a switch here. We can use another resistor box here. This is battery P, this is switch S. And then you can have the other circuit. Right. So this is the new one, the new resistor, additional resistor. Why is that? Couple of things. Understand, first one, sometimes when you take the readings might go to a corner. You might have a very small value to read. And if that is the case, that means the fractional error in reading is going to increase. So better if we bring the reading to the middle. So if you are getting a very small value to read, meaning the voltage drop across the string is much bigger. Imagine the battery you are comparing is 1 voltage, whereas you have the voltage drop across the string is 10 voltage. Then you just need 1/10 of the string, which can be a small length. So what we must do now, we must reduce the voltage that drops across the string. How do you do that? Increase this resistance. So that if we can bring down the voltage that drops here to 2 voltage, then if this is 1 voltage, somewhere in the middle you will get the balancing point. Then the fractional error of reading will be less. Point number 1. Point number 2, if you want multiple readings to draw a graph, there is nothing else you can change. By changing this resistance, you can change the current through this, which means you can change the potential gradient, potential drop on this line. So you write like E equals KL, that K will change time to time. That will help you to take multiple pairs of readings for L1 and L2 and go for a graph if you want. Clear? So this is the advantage of having a variable resistor box or variable resistance at this point. Clear? Cool. So that is also another straightforward based on the practical only, like within the practical framework, within whatever we have done, they have asked few questions. This was 1987 paper. Right? Now let's take a more recent paper and see how it has been tested. There is 2005 paper with the same question. Right, 2005. A partially drawn incomplete arrangement of a potentiometer circuit used to measure electromotive force of cell is shown in the figure. What are the items that you need to use to protect the galvanometer from high currents and to perform this experiment accurately? What items do you need? A high resistance, and a switch, or you can say plug key, insert key or plug key. Next, we are very familiar with the arrangement. Yes. Complete the given circuit diagram, adding the two items mentioned in one above and showing the connections. Right. Let me keep the switch here. Right. Since I had less space, I kept the switch there and the resistance here. Right. Let's call it R. So what you do, you keep the switch open, so the current will flow through the resistance. And then once you have found the approximate balancing point, close the switch. In the potentiometer circuit shown, the length and resistance of the potentiometer wire are 600 cm and 8 ohms respectively. And E naught is 2 volt. Internal resistance of the accumulator is negligible. The potentiometer is needed to be modified in order to measure small voltages of the order of millivolts instead of E. If you are provided with a variable resistor R, show on a circuit diagram how you would connect this resistant to modify the potentiometer circuit to measure small voltages. Now look at this. Here E naught is how much? 2 voltage. 2 voltage. So what will happen? Entire 2 voltage will fall across AB. So if you want to measure a few millivolts, the balancing length is going to be somewhere like in the corner, like very close to A you will have it. Because 600 centimeter is going to have 2000 millivolt. So 1 centimeter will have 3 millivolt. Suppose you want to measure 10 millivolt, you will have approximately 3 centimeters. Right, in 600 centimeter, when you measure 3 centimeter, fractional error can be, usually 1 millimeter is the error, right? 1 divided by 60. It can be a significant fractional error. To avoid that, what we must do, if you want to measure in millivolts, then you should reduce the voltage that falls across AB. Reduce the voltage across AB. How do we reduce it? Put another resistance here. That's what they are asking. So we'll have the battery and did they say variable resistor? Yes. So, let us say variable resistor and the switch is already there. That is it. This is going to be A, B, E naught, E naught. Have they given a name for this? R. So, previous one, let us not call it R, let us call it R dash. Okay. The figure shows a part of an experimental setup with the above potentiometer circuit and a thermocouple arrangement used to measure the specific heat capacity to molten tin. Heating coil is H. This is heating coil. S, a well-lagged container with molten tin, right. If it is desired to have a potentiometer drop of 40 millivolt across the full wire length of potentiometer, what is the value of the resistor R that you should use? So, understand now the R and this resistor, the potentiometer string are going to be in series. So, I can say this way, 2 voltage is going to be with this the resistor that we used R and the potentiometer string which has 8 ohm resistance into 8 has to be 0.04 voltage. Why 40 millivoltage means 0.04. See, 2 voltage I am dividing according to the proportion of resistances R and 8. R and 8. Okay. Now you can change it or solve it. R plus 8 goes up there. This is 16 by 0.04, that is 1600 by 4, 400. So, R has to be 392 ohms, 392 ohms. Clear? The balanced length at certain instant, sometimes after heating coil was turned on, was observed to be 240 centimeter. Find the thermocouple voltage in millivoltage at that instant. Now, you know 600 centimeter, the voltage drop is going to be 40 millivolt, 40 millivolt, 40 millivolt. So, for 240 centimeter, let us say thermocouple voltage 40 millivolt for 600 centimeter. You want it for 240 centimeter. So, this is like a voltage gradient into 240 centimeter. For that is 16 millivolt. 16 millivolt. You get 16 millivolt. Using the graph shown of the thermocouple voltage V naught versus temperature theta, find the temperature of molten tin of the instant mentioned in C2 above. Right. They have given V and theta, temperature. Right. Voltage now we have got it, it's 16 millivolt. 16 millivolt. Let's draw the 16 millivolt line. 16, 10, 15, 16. Yes. And this is 200, 290, 290. So, according to the graph I have here, it's 290 degrees centigrade, 290. Okay, that's how you get it. You know the voltage and check the temperature, 290 degrees. So, check the graph carefully, like the graph I have here is like that. Sometimes what you get in the exam paper would have been slightly different. So, whatever the graph you have, check the voltage, draw the line and see what reading you get here. The balance length was obtained again 2 minutes later and its value was 360. So, earlier it was at 240 centimeter, now it has gone to 360 centimeter. That means voltage has increased. Voltage increase means the temperature should have increased. Why? Look at the graph, voltage and temperature. Right? Even if you don't know thermocouple, by looking at the graph you can understand temperature and voltage have some connection. Right. So, if the mass of tin used is 375 grams and the power of the heating coil is 100 watts, calculate a value for the specific heat capacity of molten tin. Neglect the heat capacity of the container. So, simple, we are going to assume we know the heating coil's supply capacity. So, the heat supplied in 2 minutes must be equal to the heat gained in 2 minutes, right. For that, let us find the temperature. To find the temperature, you need the voltage. So, let us say now voltage is V theta dash, 40 millivolt is for 600 centimeter. Now, they are asking for 360 centimeter. That is 640, 24 millivolt. 24 millivolt, right. Let us go and check for 24 millivolt. 24, 24, right, 24, the temperature has to be, this is 440, 440, 290, 440. So, it has gone up by 410, 20, 30, 40, 50, yes. So, it has gone up by 150 degrees, 150 degrees. So, let us say heat gained should be equal to heat supplied. Heat gained MC theta, M 375 over 1000, S we do not know, MS theta, theta from here you can say 290, 440, 150, 150, 150. Heat supplied 100 watts per second, 100 joule, 2 minutes, 2 minutes means 120 seconds. Solve this, you must get the answer for S. How do we solve it? If you cut it by 3, it's going to be 125. Yeah, so S is going to be, look at this, ms delta theta here. So, this is 4 into 10 to the power 3, this 10 to the power 3 also goes, let us say 4000, 1000, 125, 150, 125, 150. So, you can solve it, 125 and 1000 will be 8, am I right? See, S is going to be 4000 here, this 1000 went up, right. 150, cut it by 550, it will be 3, you will have 80 here. So, you will have 5, this is 8, correct, 125 and 1000 will be 8. So, 640 divided by 3, that is 213.3 joule per kilogram Kelvin, joule per kilogram per Kelvin, correct. So, that is what we get the answer for the specific heat capacity of tin that they have used here, clear. So, not that complicated, bit of knowledge from heat is required here, but not that difficult, you write that and you get this answer.